Good afternoon, everyone. Can you hear me okay? Great. So this is our last class. We've got our final exam on Friday. You're going to be able to take it any time on Friday, and you'll have 2 hours to take it. And I'm planning on having 25 questions on there, multiple choice. So that gives you 4 minutes and 48 seconds per question. And the final exam is comprehensive. It'll cover all the material from the course, and I'll review everything today. If you have any questions, feel free to ask them. I guess before we get started, I hope you enjoyed the course, and apologize again that we couldn't include any of the practical and applied parts of the course. But if you're interested in this stuff and you'd like to work on a research project or do an independent study, I think most of you are probably juniors, so if you're interested in working in my lab next year, then contact me, because this is the kind of stuff that we do, except it's obviously more applied than theoretical. But this is this course gives you I think a pretty good taste of what we do. Okay, so the first thing I want to cover is quiz 8. So let's go over that first, and then I'm going to finish up the last lecture, and then to review for the final exam, I plan to just run through all of the quizzes, because I plan to basically adapt quiz questions and make them exam questions. So I think that's a good way to review for the final exam. Okay, so quiz 8 starts out asking, hopefully you can see that okay, you should see the slide. What are 2 operations that you can perform on System Verilog code? The answer is simulation and synthesis. Simulation is for debugging and validating the design, but the simulation doesn't give you any information about the delays, the logic delays. So in a simulation, in a behavioral or logic simulation, all of the gates have basically lambda delay, epsilon delay, which is greater than 0 but infinitely small. Whereas in a real system, of course, there would be logic delay due to the resistance and capacitance. And then synthesis is when you take a HDL design and you convert it into a form that can be implemented, that can be mapped to physical hardware. I had fun coming up with the fake answers here: analysis and cross-check, refactoring and modularization, mapping and design rule check. I made those up. Okay, question 2: what is the problem with the System Verilog code, System Verilog module below? And I'm sorry, I left some escape. Some backslashes in there. Okay, so this says it's a module called myfunc. It has 3 inputs, A, B, and C, and an output Z, and there are 2 assign statements in there. So what's the problem? The problem is that there's the assign statements both assign Z. So you have 2. So this is kind of hard to explain, and I know that this is kind of confusing. I know it's confusing because in my other class, 611, some students have a hard time understanding how the code is decomposed into actual logic gates. You have to kind of imagine that every one of these assign statements represents a logic gate, essentially. And so because I have 2 assign statements, you'll end up having 2 logic gates whose output is connected to Z. The other thing you have to remember is that Z isn't a variable. Z represents a signal or a physical wire. So you have two logic gates that correspond to each of these 2 lines of code, and these lines of code are not executing in any particular order, because they represent 2 logic gates that would be operating concurrently, and they're both driving the signal Z. So signal Z is potentially in conflict. Now, if they both If A, B, and C are all 1, then both assign statements will assign 1 to Z, and I think the simulator will be fine with that. You'll just see a 1 in the simulator. But if C were 0, so if A and B are 1 and C is 0, then the first line would assign Z to 1, and the second line would assign C to 0. So you'd have a conflict, and in the simulator you'd have a big fat red X for Z. So you don't want that. Now I mentioned that there is a way you can get around that using the high impedance value. So I could have I could use a ternary operator in here and assign and have a design where only one of these lines of code assigns a 1 or 0 to Z, and when that happens, the other one will be assigning Z the high impedance, and that would be okay. Although to be, in my experience doing that, at least on an FPGA, using Z high impedance, pretty rare. I'm not even sure how well that's supported on an FPGA, to be honest. So generally, you don't double drive a signal. You want to avoid that. The system Verilog supports structural or behavioral HDL. It supports both. Now, in this class, though, we basically covered only one way to do behavioral HDL, and that's through the assign statement. And most of the stuff we talked about in this lecture is structural, how to instance and connect modules together. But that's basically how, in terms of what we discussed, the assign statement is behavioral, and all the connecting stuff together, that's structural. How many possible values can be assigned to type logic? There's 4. There's 0, 1, Z, and X. I mentioned VHDL has more, but in Verilog there's only 4. I prefer having more because the problem is Z means different things. I'm sorry, not Z. Sorry, scratch that. X. The value X means different things depending on the context. X could mean conflict. It could mean undefined. So I don't like that there's only 4. There should be more than 4. I think VHDL has 6 or more because there's U and dash, U and hyphen. But anyway, yeah, in Verilog there's 4. Consider the following system Verilog modules. Okay, now these represent 2 modules, and this is a mixture of structural and behavioral HDL. We have an assign statement in here, and we have an instanced module of bottom, which I called my thing, and there's some wires connected to it. I mentioned, I think last lecture, I talked about how when you have multiple modules, you have to infer the design hierarchy. You have to figure out what the relationship is with these modules. And so you notice that bottom doesn't instance anything. It's just behavioral code. It's just an assign statement. So it's a leaf node. It's a bottom. It's the bottom of the hierarchy. But top instances bottom. So top in this case is the top of the hierarchy, and bottom is the bottom, which, that's why I named them that way. But they won't necessarily be named that way. So in top, we've got 2 internal signals, Y and A. There's no inputs and outputs on top. But there are 2 internal signals, Y and A. We assign Y to 1, and then we connect Y to the A input on bottom, and we connect A to the Y output, which is basically confusing because we've got Y and A in top, and we've got Y and A in bottom, but because of the way we connected them, the Y and A in bottom are swapped as compared to top. So basically, inside of top, we've got Y is the input and A is the output, and then in bottom they're reversed. So in bottom, Y is equivalent to A in top, and A is equivalent to Y in top. And that's simply because of the way that we connected these guys, right? So the dot A represents the ports on bottom, and then Y and A in parentheses there represent the actual connections to that bottom. So the question is, what is the value of A and Y within my thing? What is my thing? Well, my thing is the bottom. My thing is the instance of bottom. Now you might say, well, why did you say my thing? Why didn't you say bottom? Well, bottom's the name of the module, so I could have like 10 bottoms instance instead of top, and they would all have their own names. So whenever you're talking about hierarchy, you have to talk about a specific instance name. So that's why I was very careful here to say my thing, what is the value of A and Y within Y thing. So if I drill down inside of my thing, I get inside this bottom module, because that's what thing is. It's a bottom module. And inside there, A is going to be whatever Y is in top. So Y is going to be 1. And sorry, Y is, now I'm confused. Y is going to be, so A inside here is going to be whatever Y was in top, right? So A is the input. A is going to be 1, and of course Y will be not 1, 0, right? So let's see, it should be, A is 1, so it should be 1 and 0, right? Yeah, 1 and 0 for A and Y respectively. So that's, is there a default value that will be assigned for logic data type? No, no. If you don't assign it, it'll come up as X. You have to assign it. Yeah, you have to assign it. Now, in this case, normally at the very top level, all of your inputs are assigned by external pins. But in this case, top is assigning things. Top doesn't have any inputs and outputs, which means that top is basically a test bench. I didn't talk about test benches, but top is not something like what I've got here in top is probably something you wouldn't convert to hardware. That looks like a test harness, judging by the fact that it doesn't have any top level inputs or outputs. Normally, in your top level module in Verilog would have inputs and outputs that would map directly to the pins of the chip. And then, you'd connect those from the outside of the chip, outside world, from the circuit board. But yeah, this one is this is confusing because they're basically, the idea is that A and Y are swapped because of the way the port map is done here. Okay. Next question is, how many bits are in the following constant number? This one's easy. It's 11. It's just 11 apostrophe is the number of bits, and then B stands for the base, and then 1 is the value. I didn't need to put that 0, 0, 0 there. The leading zeros aren't necessary. I don't know why. I mean, it's not going to hurt anything. I don't know why I put them in. I think just to make it a little confusing. But you could just put 11 apostrophe B1. It would be the same thing. Okay, to what is the value of B set in the system Verilog snippet below? Okay, so this is question 7. I did not cover this in the last lecture, and yet I still asked you a question about it. So in the quiz, no matter how you answered this, you will get it right. I marked all the answers as being correct, just because I never covered it. Although I looked at the grades, and it looked like well, I think 62% of you got this question right, but that's actually not 62% of you. It's 62% of all the attempts, and you get 2 attempts, so it's kind of hard to figure out what the percentage of the final submissions, final values of the quiz. But anyway, it looks like you guys figured this out. That's what I'm trying to say. But this one is doing some bit operations, and I'll talk about these right after I get through the quiz. So you've got A and B are both 4 input values, and A is 4 bits holding the decimal value 3, which in binary would be 0011. And so I'm going to take the 2 rightmost bits of A, bit 1 and 0, which would of course be 1, 1. So the 2 rightmost, or the 2 least significant bits of A, is 1, 1. And then I'm going to duplicate those 2 times. So I'm going to take the least two significant bits of A, concatenate them with this comma and the curly braces, and then I'm going to duplicate those twice. So it should be 1, 1, 1, 1. So that's the answer there. But no matter, you should have got that right regardless of how you answered it. How many bits comprise the signal A in the system Verilog snippet below? That's easy, 4. If you got this wrong, it might have been because you saw 3 and you said 3. And this, I mentioned last lecture that this to this day throws me sometimes. You look at this thing and you say, oh, 3, it's a 3-bit signal. Well, it's 3 down to 0. It includes, it's bits 3, 2, 1, and 0. There are 4 total bits. I don't know why they use this crazy, needlessly misleading syntax. but you have to get used to that. This is 4 bits. So every time you have a n bit signal, you declare it as n-1 down to 0, or n-1 colon 0. To what value is A set in the system Verilog snippet below? This one is kind of just a confusing assign statement. So this is, oh, okay. So you have to be careful here because there's a ternary operation. Now ternary has the lowest precedence of any operator. But the problem is now we're combining a shift in here with a equals, right? So which one gets done first? Do we do the equals and then the shift, or the shift and then the equals? I don't know. I don't remember. Is it the shift? Okay, yeah. Normally I would just refer to the slides, but it's a pain to switch between. It's a pain to shift between windows here on Blackboard. So I'm gonna say shift. Okay, so let's see if that's right. So we're going to take the value of 2, we're going to shift it 1 bit to the left, that multiplies it by 2. So 2 multiplied by 2 is 4. Now this is weird though, right? Because how many bits, let's say I do the shift first. Okay, I got a 2-bit signal and I'm shifting it by a 1-bit signal. So how many bits is the expression? Because see, if the expression evaluates to 2 bits, right, then 2 shifted by 1 bit to the left doesn't fit in 2 bits, right? This is going to be 2 multiplied, this is 4, but 4 doesn't fit in 2 bits. Or is Verilog going to assume that this sub-expression will evaluate to 3 bits because I need 3 bits minimally to represent the answer? Well, unclear, but let's just assume that it's going to say 3 bits. Let's just say this will be, I'm just going to assume that Verilog is going to just break all the rules and add wires indiscriminately. So this will be 2 times 2 is 4. I'm going to check to see if that equals 4. And if it does equal 4, then the whole ternary will evaluate to 1, otherwise 0. So let's see, is it 1? Yeah, it's 1. I looked all this up when I wrote it, but I already forgot. I already forgot how to do it. Yeah, parentheses would have helped, but I was deliberately trying to make it confusing because it's a quiz question. But yeah, in practice you would put parentheses. Yeah, exactly. And as Charles said, this is normally I would check the precedence table. To this day, I still when I write code in C, I'm always checking the C precedence table because I can never remember if the dereference operator has higher priority than the indexing operator. When you work with pointers, it gets confusing, and I can never remember it. Never can memorize the whole table. But anyway, I think that's the last question. Oh yeah, and one more. Yeah, sorry, one more question. So in the system Verilog code snippet below, to what value is signal A set? This is another bit manipulation one. I should have gave everyone credit for this one too. I think I'll do that. Yeah, let me do that. Question 10. Yeah, I missed this one. So again, it's taking, in this case, it's a 4-bit octal value 10. So an octal, this would be 8. So this is octal is base 8. So 10 and base 8 is actually 8. 1 0 0 0. 1 0 0 0 in binary. And then I am assigning that to, now this is kind of cool how you can do this. You can use the concatenation operator on the left-hand side of an assignment. That's crazy. I don't know, you probably can do that in Python too, but I think it's neat. But anyway, basically, I assign it to bits 1, 0, 1, 2, 3, but because these are listed in the 0 on the left and 3 on the right, this is going to have the effect of reversing the bit order. So the right-hand side of the expression is 1 0 0 0. The left-hand will also be 1 0 0 0, but it's going to map those bits in the opposite order. So A will will be assigned in reverse order, so it'll be 0, 0, 0, 1. All right, so it's basically reversing the order of octal 4 bits, value 8. So that's that's another bit manipulation, and I'll give everyone credit for that one because I didn't get to that either. Okay, so that's quiz 8. Alex said, so in reality, would it adjust to 3 bits? I believe so. Yeah, I believe so. The problem, though, is the problem is that A is, so the problem here is that A is 1 bit, right? And in fact, the whole expression will evaluate to 1 bit in the ternary. It says 1 bit 0, 1 bit 1, 1 bit 0, right? But the problem is that inside the ternary, you need 3 bits. So yeah, so apparently this is from last year. I grabbed this question from last year's quiz. I'm sure I tested this. And that's how it acted. But that's a tough one because it's kind of vague. It's vague with regards to how many bits the sub-expression would evaluate to. Okay. Yeah. In fact, that's yeah. I mean, I guess you could argue that it might be possible that it would generate an error. I'll have to double check that. Make sure that's correct. I mean, just double check, test it in the simulator. Okay, let's now switch over to share. I'm going to switch back over to the system Verilog. Okay, pop up. Come on. There it is. Okay. So I mentioned we didn't cover very much of System Verilog, but I think this will give you a nice introduction for 611. I think this is gonna, I think this will be helpful for 611 because we go into much more detail in 611. So this is just intended to be an introduction. So I mentioned in the quiz there's simulation and synthesis. There's behavioral and structural modules. You have modules. Modules are behavioral elements because they're intended to be connected together in a structure. So modules have inputs and outputs, and when you instance them, you connect them. They're kind of like having classes and objects. You know, you instance an object, instance a class as an object. Logic is just talked about. There's 4 values. It's intended to be a binary value, but there's 4 values to help you with, well, the X is kind of designed for simulation purposes. But also X is, like I mentioned, X is also used as don't care. So you can assign a signal to X inside your code if you want it to be a don't care. That can help with the optimizer. Z is high impedance, also for design purposes. You can actually drive a signal to Z, and that should generate a tri-state. A tri-state. Simulation is usually the output of a simulation is usually a waveform. Synthesis is when you convert this to gates, convert code to gates, or look up tables in the case of an FPGA. Whatever the primitive hardware elements are. Let's see. We talked about syntax. We talked about connecting values to pins on a module. And let's see, we talked about the assign statement. Okay, so here's another example for you. How many total bits comprise the inputs to module AAAA? In this case, there's 2 total bits because there's A and B are the 2 signals, and each one of those is a bit because they're logic. There's no brackets here, so there's no if A and B were multi-bit signals, then there would be the bit ranges between logic and A here. And then this question is fill in, the next example is same module, but fill in the missing values for the test vectors. Now I didn't talk about test vectors much other than to say that they are inputs and expected outputs for testing a module. So if I want to test AAA, in my mind I know how it's supposed to work, but I want to make sure that the design is working the way I expect it to. So in this case, there's only two bits. I can test every possible input combination, all the enumerations. So A and B 0, 0, 0, 1, 1, 0, 1, 1, and then C would just be a 1 whenever A is 0 and B is 1. It's just based on this Boolean expression here, and 0 in every other case. And then let's see, in the system Verilog code, what is the value? To what value is A? To what value is signal A set? This is the same thing we had in the quiz, basically, right? Yeah, this is where you have A and Y are swapped through the hierarchy. And then in this case, this next example is a little different because I added an assign A equals 1 in the module top. So inside of top, I'm driving A with an assignment statement, but I'm also driving A with the output of my thing. So Y is an output. Now, the problem is, this is one thing that's another little kind of irritating thing about Verilog. You notice that in the bottom, when I declare bottom, it's really clear where the inputs and outputs, what the inputs and outputs are here, right? And it's even more clear if you put them on their own lines, right? Like if I were to hit enter, put a new line after each one of these individual inputs and outputs. But when I instance my thing, which is a bottom module, and I connect its inputs AI, it is not obvious what the inputs and outputs are here when I instance the bottom module, and I don't like that. You can't tell from looking at the top. When you look at this top module, if you don't see the bottom module, if you don't have them kind of both on your screen, you don't know what the what are the inputs and outputs? Unclear. You just know that there's A and Y. I don't know what they are. So obviously you could put comments in there, or you can give them names that make them obvious what they are. But if all else fails, you have to refer back to the module that you're instancing to see what the inputs and outputs are. So this is a very common type of error. I mean, because notice that A is connected to an output of my thing, but yet I'm assigning it. So I have two entities that are driving A. I've got an assign statement, so I've got some behavioral code, and then I've got my thing, which is structural code. They're both fighting over A. Now, in the case of the assign, it's obvious because it's on the left-hand side of the assignment. But in the case of my thing, I don't know. It's not obvious that A is being driven by my thing. It's not obvious at all. So you got to be careful with that. And then finally, last topic is, I'm going to skip ahead. There's a precedence table. Let's see if we were right about that. Yeah, shift is higher precedence than equals. So yeah, we had that right. Thank you, whoever reminded me of that. Numbers, I think we talked about this. Basically, number of bits, apostrophe, the base, and then the value. So the base options are binary, hex, and octal. Oh, and decimal. So B, H, D, O. This is different from Java and C. And okay, last topic here is bit manipulations. So there's basically three things you can do with bits. You can do concatenation, you can do slicing, and you can do duplication. And you could do reductions. Do I have reductions on here? I do, but I'm not. I'm just going to talk about concatenation, slicing, and duplication. So concatenation is when you have signals that you kind of glue together. In this case, I'm assigning Y to be bits 2 down to 1 of A. Notice I put this expression inside of curly braces. That's necessary in order to concatenate. You need the curly braces. And then inside the curly braces, you separate each component of the signal with commas. Now the problem is that when you look at this, it might be tricky to figure out how many bits the right-hand side of this assign is comprising, right? So I've got 2 bits of I'm slicing out 2 bits of A. So notice I use the parentheses 2:1. So I take bit 2 and 1 of A. And then I'm going to kind of concatenate it with, in this case, 3 copies of B0. So this is another syntax trick. In this case, I'm taking bit 0 of B, and I'm duplicating it 3 times. Now this one is kind of weird. So to duplicate that, I have curly braces. I have 2 levels of curly braces. I've got curly braces. The value I'm duplicating is in curly braces, and then I put the number of times I want to duplicate it to the left-hand side of that. and then I put another set of curly braces around it. And you have to do that to duplicate. You need both sets of nested curly braces to duplicate. And then I tag on an A and then a constant comprising of 6 bits. So this will be converted, essentially will give you a value of Y that's going to be A bit 2, A bit 1, and then three copies, right? Yeah, 1, 2, 3 of B bit 0, and then a copy of bit A0, and then the value 100010. So these will all just get concatenated into one value and assigned to Y. Now, hopefully, Y is wide enough to accept this value, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bits. So hopefully Y is 12 bits. If it's not, if it's more than 12 bits, I believe Verilog will zero pad it on the left-hand side. If it's less than 12 bits, then you'll probably get an error. You want to be careful, though, with that. You know, you create this signal, and you want to make sure that the left-hand side and the right-hand side have the same width. The width of the right-hand side is implied. Width of the left-hand side would be however you declared Y. I mentioned in the quiz, too, the last question, you can actually put the concatenation on the left-hand side of the assignment, in which case, in this case, we hope Y is 3 bits. So if the right-hand side is 3 bits, the left-hand side is also 3 bits, because I'm going to take whatever's in Y and assign the least significant bit of Y to the least significant bit of B, and then bits 2 and 1 of Y will get assigned to bits 2 and 1 of A. Oh, and notice the underscore. I forgot to mention that. Notice there's an underscore over here on this constant. Those are actually ignored by the compiler, but they're useful for the designer to put in as a way to split up constants into fields. So in this case, I've got these, you know, 2 sort of distinct fields that are 3 bits each. I don't know why. It depends on the, you know, the context. I don't know what the context is. Okay, so here's another example. This is a concatenation operator that I'm using to sign extend. I'm taking B, which is a 16-bit value, and I want to take the sign bit, which is B15, and I want to duplicate that 16 times. So this will sign extend B. Sign extending is when you have a 2's complement value, and you want to convert it from one bit width to another bit width that is wider than the original one. So in this case, I want to go from 16 bits to 32 bits. I need to figure out what those other 16 bits are in the output. And so because I'm, you know, the idea is I want to take the sign bit and duplicate that and use that to fill in the upper 16 bits of B extend. So that's how I used to do it until I did it like this for a long time, years, before I figured out that you can use this duplication operator, which does the same thing. So in this case, this bottom line does the same thing, except instead of me having to say B15, 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 now I can just say take B15 and duplicate it 16 times and use that to fill in the other 16 bits of the extended version of B. Okay. What value will the following system Verilog code set to signal B when A is 0, 1, 0, 0, 0? So in this case, I'm going to take B, and I'm going to set it to be bit 0 of A, so 0. It's rightmost bit. Bit 1 of A, which is 0, and then duplicate bit 2, which is 1, 2 times. So it would be 0, 0, 1, 1. And then another example, which of the following system Verilog statements takes as input an 8-bit value and produces an 8-bit output value, where the upper 4 bits and the upper 4 bits, I think there's a typo in there, I'm sorry, where the upper and lower 4 bits are swapped, sorry. Which of the following system Verilog statements takes as input an 8-bit value and produces an 8-bit output value, where the upper 4 bits and lower 4 bits of the input are swapped? So we want to swap. So eight bits come in, 8 bits go out, but I want to take the upper and lower 4 bits and swap them. So which one is doing that? Looks like 2, right? So I'm going to take A 3 down to 0 and A 7 down to 4, which are the upper and lower, but I'm going to position the lower 4 bits on the left-hand side and the upper 4 bits on the right-hand side. So this should swap the upper and lower 4 bits. Excuse me. Okay. Okay, so yeah, I'm going to just go ahead and stop there. So all you need for the exam is to know your structural Verilog and the assign statement and the bit manipulations, which are, like I said, the bit slicing, where you use the brackets to extract individual bits or ranges of bits, like as I do here with D0 3:0, and as I did over here. So this is a bit slicing or bit extraction. Duplication is this double nested curly brace thing, and the concatenation is the curly brace with the commas. Any questions about that? Okay, so I'm going to switch over now to, I'm going to go all the way back to quiz 1. And I want to run through these. Now, I'm trying not to make this too boring. I'll run through these kind of fast. And if you have any questions, feel free to ask. It's been a while since we've seen this. Okay, so you should see quiz 1 here. There it is. Okay. So remember, the first topic we covered was interfacing protocols, system-level interfacing protocols, chip-to-chip protocols. We talked about some general stuff about synchronous versus asynchronous. So this question says, if you have 3 wires D in, D out in clock, is it synchronous or asynchronous? Well, you can be fairly confident that it's synchronous because you've got a signal in here called clock, and when you have a clock inside of the interface, it's synchronous, right? So likely synchronous based on the signal names. Chip transmits 8 bits to its peer. How many bits does it receive in return? Well, there's no way to know. It depends on the protocol. Some protocols like SPI will send 8 bits back. Other ones like I2C, I2C might if you're doing a read. But so it's impossible to tell from the information given. UART channel runs at 57,600 baud, has 16 data bits, 1 start bit, 1 stop bit, and 1 parity. The start, stop, and parity are overhead bits. So to calculate the actual throughput, you take the baud rate and you multiply it by the number of data bits divided by the total bits per transaction. So the transaction in this case is where you add the start, stop, and parity bits to the data. So in this case, you're transferring 16 bits because there's 16 data bits, but it requires 3 additional bits, start, stop, and parity, which is 19. So it's 57,600 multiplied by 16 over 19, which is 48,505. This is another UART. What value is received in the timing diagram below? Make sure you're comfortable with these timing diagrams. Basically, the first bit is start. Now, notice that you might say, well, how do you know where the bit starts and ends? Well, there's dotted lines here, but also you can tell from the smallest time between 2 transitions is going to be 1 bit time. Now, you might say, well, what happens if you never send 1 bit in isolation, 1, 0, or 1 in isolation? Well, then that could be tricky. But we know that there's 7 data bits and there's no parity and there's 2 stop bits. So we know that the time between these gray areas is divided into 7 plus start and 2 stop bits. So there should be 10 intervals inside of this transaction, where each of the interval is a bit time and they're all equal length. So the first one is, you got your start, and then the question is which value is received. So we're going to go off of the RX, the receive, and it's least significant bit first. So we have to read these bits in reverse order because it's least significant first. So we're going to ignore the stop bits. We're going to ignore the start, and we would normally ignore the parity if we're just trying to extract the data, but there is no parity. So the answer is 7 data bits. Now, again, a little confusing because we have to read from basically right to left, but you have to group. If you're doing this in hex, you have to group in 4 bits, starting from the least significant to the most significant, right? So basically, the first hex digit is going to be the first 3 bits, reading from right to left, which is going to be a 0, and then the next one is going to be 1101, which is a D. So 0D. So it's 0D. You might say, why 2 hex digits if it's only 7 bits? Well, you can do that. It's fine. But the most significant hex digit would be a value between 0 and 7. In this case, it's 0. Okay, what bit is missing? Let's see, in the timing diagram, well, we only care about, there's only a bit missing in transmit, so we only care about the transmit side, and it's odd parity, and so the total number of 1 bits is 1, so the missing bit needs to be 0, because if it was 1, it would give us an even number of 1 bits. So there's the start bit, basically between the start and the stop, including the parity in the data, we have 1 bit. So in order for that to be odd parity, the missing bit must be a 0. For an SPI channel with C-pool equal 1 and C-FA equal 0, when does the data signal change? If C-pool is 1, it means the first edge is falling because the clock is 1 by default, and if C-FA is 0, it means that if C-FA is 0, it means the data is ahead of the clock, which means the data will actually change before the clock changes. So the first edge of the clock is, when does the data signal change? The data signal is going to change before the first falling edge of the clock. And the idea is that with C-FA 0, you're going to sample the data on the first falling edge. The idea is that when the clock falls, the first falling edge, the data has already been established on the data line because it had already changed one half clock cycle earlier. So yeah, the data would have changed before the clock changes for the first time, which will have been a falling edge. What percentage of an SPI channel's master to slave bandwidth can be utilized when performing a series of single write transactions? It's 100% because in SPI there's no overheads. There's no start and stop bits, no parity bits. The transactions are controlled by the slave select and the clock, so in theory the master could just hold the slave select down. In a daisy-chained SPI connection between master and N slaves, how many clock cycles are required to complete a full exchange? Well, if you have 1 slave, it takes 8 bits, 8 cycles. Sorry, 8 cycles, not 8 bits. 8 cycles. If you have 2 slaves, it would be 16 cycles. With N slaves, it would be 8 times N cycles. So this is a daisy chain where basically the master sends bits into the first slave, and then the first slave sends bits into the second slave, and the second slave to the third slave, and then eventually when you get to the last slave, it goes back to the master. So this is one way to do multi-slave SPI, multiple slaves with one physical SPI interface. What is C-pool and C-FA for the exchange? This one's easy because C-pool is just basically the default, the starting value of the clock, so it's 1. And then for C-FA, you just look at when the data changes relative to the clock. In this case, they both change at the same time. The data is not ahead of the clock. It's at the same time as the clock. So that means that C-FA is 1. So 1, 1. So the start, clock starts high, it means C-pool is 1. First change in the data corresponds with the first change. The first change in the data corresponds with the first change in the clock. Which means that C-FA is 1. What data is written in the transaction below? Okay, so now this is so this is what data is written. So this one's a little confusing because this is a transaction, an SPI transaction, which includes two exchanges. The first exchange is the address and basically the header that the master sends over, and then in the second exchange is when you actually do the write, assuming it's a write operation. So you have to first kind of identify the two exchanges here. So you have to count 8 cycles. The first 8 cycles are for the header. Second 8 cycles are for the data. So in this case, the data is in the second 8 cycles of the second exchange, or the second 8 cycles of the transaction. Finding where the bits are, where to read the bits, is tricky with SPI. So you need to basically figure out which edge of the clock the data is valid on. In this case, the data is valid because of this combination of CPOL and CFA on the rising edge. You don't want to look at the falling edge because that's when the data changes. The data is in flux on the falling edge, but on the rising edge of the clock is when the data is stable. So notice I put these little 1s and 0s here right on the rising edge, which also happens to line up to these dotted lines, which is nice. So yeah, so now you might say, wait a second, I mean, how do you know it's doing a write? I mean, which bit in the header tells you it's a write? I don't know. That's application specific. That's not built into the protocol. But I'm going to infer from the question that it's a write, because the question said what data is written. So I don't really care about which bit in the header tells the slave that it's writing, because, well, also you can see that MISO is flat too. So you can see that if this were a read, then there would be data coming back from the slave on MISO. There's not. So this is clearly a write. So I don't really care what bit in the header signifies that it's a write as opposed to a read. I'm just going to go ahead and grab the bits in the second exchange. Okay, that's the first quiz. Let's see, I'm going to have to speed up here a little bit, or I'm not going to get through all these. But that's okay. The important ones are the earlier ones that you might have forgotten about. So if I don't get through all the later quizzes, I think we'll be okay. Okay, so this is quiz 2. This one had 20 questions on it. Come on. There we go. Okay, how many bits are sent in each direction in SPI exchange? This quiz, by the way, was mostly just kind of just general questions. There's a few waveforms on it. But how many bits are sent in each direction in SPI exchange? 8. You might say, well, why? Who cares? What's the point of this? Well, the point is what is an exchange versus a transaction? It's a terminology question. Exchange is 8 bits. Transaction is multiple exchanges. For an SPI transaction consisting of a write operation, how many bytes are sent from the slave to the master? Well, it's a write. So master sends the data on a write. There's nothing, say, sent from the slave. Doesn't send anything on a write, so 0. Now, this one's a little misleading though, because an exchange. You could argue, well, it's an exchange, so technically, even though you're doing a write, the slave does send bits back through the SPI channel. Yeah, but if you're doing a write transaction or write operation, you're going to ignore those. You're going to ignore. You're just doing a write. So the slave, yeah, technically gets bits back, but they're ignored. So. So logically 0. For a multi-bit SPI channel that has 1 SS signal for each slave, how many slaves can transmit at a given time? Okay, now this one, multi-slave, but not daisy-chained, 1 SS signal for each slave, 1 slave select. So if that happens, only 1 slave can transmit. And the reason for that is because all the slaves are going to be connecting their MISO, master in, slave out. So the slave's output is MISO. They're all going to connect their MISOs to 1 wire. So they're going to be this is a wire that's going to be potentially multiply driven. Now, I mentioned in the lecture that this is a case where you'd have to use a high impedance. You'd have to use a tri-state. So the assumption is that only 1 slave is actually driving the wire, even though they're all connected to that same wire. Now you might say, why? Well, why not just have more than 1 MISO wire? Huh? You can if you only have 1 SPI channel. There's only going to be 1 channel you can have multiple SS, slave selects, but one channel implies that there's one MISO and MOSI and one clock. So the slaves are all sharing one wire. Only one can send at a time. What is the result of two devices driving a and by the way, you might say, well, how does the slaves know which one? Well, which one should get mastership of the wire? Well, it's based on the SS, the slave select. What is the result of two devices driving a single wire to logic 1 using a push-pull? Well, in the case of push-pull, you don't want to have multiple devices with push-pull on one wire. But if you did have two double driving a push-pull, then it's good to have them both setting to logic 1 because basically that'll be fine. You can have two devices driving the same wire if they're both in agreement. The problem is when one tries to pull up and one tries to pull down, then you've got an issue. In this case, it's okay, but it's probably a bug in the design if this is what's happening, but it wouldn't necessarily blow anything up. What is the result of one device driving a wire to logic 0 and another device driving the same wire to logic 1 using an open drain? Okay, for open drain, driving a wire to logic 1 means you don't do anything. So basically, each device on an open drain is only basically able to actively drive the wire low to pull it down to 0. So if you've got one device that's thinking that it's sending a 1, it means it's not doing anything. It's not actively pulling the wire at all. And the other device is setting it to logic 0, pulling down, then the wire will be 0. So the one that pulls down to 0 will win in the sense that it will get what it wants. It will get the wire to be logic 0, whereas the other entity trying to pull it up, well, it won't be pulling it up. The one trying to put a logic 0 on there will lose. What's the start signal of I squared C? Okay, so to remember this, I squared C, remember, doesn't have a start bit. It has a start signal or a start condition or a start event. It's basically when, remember that in I squared C, the clock is a level sensitive clock, meaning that you don't care about edges. The clock is basically transmitting a bit when the clock is high, when it's a high level, which means that normally the data only changes when the clock is low. When the clock is high, you don't want to be changing the data because that's when you're actually sending the bit across the channel. But in the case of the start signal, you break that rule. So the start signal is when you change the data when the clock is high, which is normally not allowed when you're sending bits, but it's okay for sending the start signal. So remember that both both bits of the I squared C, the data and the clock, they're normally high, and so the start signal is when you drop the data when the clock is still high. So drive SDA low when SDA is data. Remember, SDA stands for serial data. SCL stands for serial clock. It's basically just data and clock. So you drive the data low when the clock is high. Likewise, the stop signal is when, again, you change the data when the clock is high, but in this case, you bring the data from low to high. So drive SDI high while the clock is high. How many times has the control of SDA changed during a single byte I squared C operation? 2 times? Why? Well, the SDA starts out under control from the master. It changes hands to the slave for the acknowledgement of the header. And then now if you're doing a read operation, the slave keeps control of SDA. And the control of that only changes back to the master for acknowledging the data. So only 2 times. So the header acknowledge switches from the master to slave, and for the data acknowledge, you switch from the slave to the master. However, if you're doing a write operation, then it's more complicated because you have to send the header, slave has to take control to acknowledge, then the master has to retake control to send the data, then the slave has to retake control to send the acknowledge, so in that case it's 3 times. There's the header acknowledge, the data transmission, and the data acknowledge. So you have to switch control 3 times. When I say control, I mean basically which entity is actually in control of the SDA. Now remember, the clock is always controlled by the master in I squared C. Only the data changes hands. Okay, what's happening in the following I squared C transaction? Now, luckily, I squared C is easy to read because it's the level sensitive clock. So when you're trying to figure out what the bits are, you can stick the bits. You just basically find where the clock is high and you find the matching bit on SDA. Now, the one problem here though is that unlike SPI that always sends 8 bits per transaction, I squared C is 9 bits per transaction because you have to include the acknowledge. So you have to split this into two 9-bit segments. So there's 18 bits in total. So I got to count 9 bits. First 9 bits, 1, 2, 3, 4, 5, 6, 7, 8, 9. I got to draw a line right in the middle to separate. So now I've got two segments. One is the header, the other is the data. I don't know who's controlling SDA by looking at this waveform until I start interpreting the bits and decoding the protocol. So looking at the header, obviously the acknowledge is the 9th bit in both. Acknowledge is 0 in both cases, which is acknowledge of 0 is good. That means it's an acknowledge as opposed to a knack and not acknowledge. And then the bit next to that is the read-write bit. Now you might have a hard time remembering this. Read-write is 0 for write and is 1 for read. So in this case, we're writing. We're writing something. We're writing this data to the address specified in the address. I squared C is most significant, the least significant, I believe. So the address would be 4F. So it's a 7-bit address. So the first 3 bits is the first hex digit. The last 4 bits is the second hex digit. So 4F. Right? So the bit is read/write. Oh, you mean the order? Yeah, the bit is read/write. It's a control bit that says whether it's a read or write. Yeah. Right. Yep. Read. Oh, I see. You put a. Sorry, I missed the. You put an apostrophe after write. That's right. Yeah. Read/write. Yeah, that's right. Yeah. That's right. Not right. That's right. Yeah. Yeah, you can think of I squared C as being kind of active low. So, read is 0, write is 1. No. Okay. So that one's kind of tricky to decode that. How can a collision between two I squared C hosts be detected? Yeah, how can you detect a collision? Well, you got to ask yourself, like, what would happen in a collision? I mean, you got two masters, two entities trying to take mastership. What's the first thing they do when they're trying to take mastership? Well, they try to do a start bit. What's a start bit or start signal, right? What is a start signal? Well, step 1 is data. Drop the data. That's step 1. Step 2, drop the clock. So there's kind of 2 phases. So my solution is, I don't know if this is how it actually works, but my solution is do the first phase and make sure no one else tries the second phase. So the first phase is drive SDA low and then check for the clock. See if anyone messes around with clock, tries to drive clock low. Because remember, clock and data are normally high. So I'm going to drive data low. I'm going to wait for anyone to mess around with clock, try to drive it low. If that doesn't happen, chances are I've got control. But you have to wait, and if both hosts wait exactly the same amount of time before deciding there's no conflict, then there's still going to be a conflict. So you might actually, it might be better to, I'm not sure actually how, I don't know. This is my idea. I think it makes sense. Especially since the other options were silly, were nonsensical. Okay, let's see. On an I2C read transaction, which side drives the clock? Always the master. That's easy. What's the limitation for adding additional devices to a single I2C channel? Leakage current on this, because it's open drain. Now, by the way, this assumes, in this actually, I should have mentioned in the question that I'm assuming that the pull-up resistor, there's a pull-up resistor in every host on the bus. Now, that is sometimes true, sometimes not. Charles actually ran into an issue with this when we were designing the applied portion of this class, because it wasn't clear when we were building a system with multiple I2C components, and it was not clear if we had to add a pull-up resistor on the circuit board, or in our case, a breadboard. He asked me about that. He's like, I mean, what's the deal? We have to put it on, or is it built in, or automatic, or how does this work? I think it turned out, if I remember correctly, that the pull-up resistor was actually inside the devices. So in that case, if you keep adding devices, you're going to have a bunch of pull-up resistors in parallel, which is going to decrease the resistance to VDD, effective resistance, and so you'll get more leakage current. Every device you add is going to add more leakage current. That isn't necessarily the case, though, if you're adding external, if you're doing external pull-up resistors. I think, and I don't even know this for sure, but I think most devices, I2C devices, have internal pull-ups, or you might be able to configure it, but that's still unclear. You have to read the data sheet for the devices that you're using. But also, there's a limited number of I2C addresses. The address space is quite limited because, you know, 7 bits basically, unless you go to extended mode. But the problem with this is that, you know, the I2C address is actually addressing the device and the internal register in the device. So, you know, there's a limited number of addresses. That's a problem. That's why they have extended mode, which I think uses a 10-bit address. But even then, that's not that many. That's only 1,024 total registers amongst all the I2C devices. Of course, you can get around that, though, if you have an address register that you write into on the peripheral. So I think that's the way generally it works, is that you only write to one. You basically write to the address register, and then you write the data. So you can get around that problem by, again, you know, instead of just using the I2C address directly, you write into an address register on the target peripheral, and then the following thing that you write is what you're trying to, you know, read or write from that register. So there's ways to get around that. And the collision rate will possibly increase too if you got a bunch of devices sharing the bus, because it's a multi-master bus. Okay, master sees a 1-bit during the acknowledgement slot of the data phase. What does this mean? Well, you know, again, this depends on the peripheral, but the idea here, given the options that I gave you, is if you get to the data phase, it must have meant that the address phase went through without a hitch, right? So it means that the right address was received, but the right data was not. If the right address was nacked, then we would have never got to the data phase, presumably. We would have aborted. So that's the idea there. How many bit slots comprise, and again, though, this depends on the peripheral. I mean, the data sheet, I think different peripherals might handle this differently. This is also a little unclear. How many bit slots comprise a single byte I2C transaction, not including the start and stop signals? How many bit slots? Single byte? Well, remember, it's 9 and 9, so 18, right? Yeah. You have 8 and 8, and then two acknowledged bits. 16 data bits, 2 acknowledged bits. What does a 1-bit signify in the read-write slot of an I2C? 1 is read. Yes, read. Read, yeah. What does JTAG and SPI have in common? Whoops. Sorry, that was screwed up. What do they have in common? Wrong answer. Serial. Yeah, I forget what the other things were, but they're both serial. They're both 4 wires, at least 4 wires. What else? Synchronous? Ah, synchronous. Yeah, synchronous. They are not. Yeah, it's all of these. Shift registers. Sorry, I misspelled synchronous. They work by using shift. They shift bits. So you shift bits in, you shift bits out. You shift bits into the slave shift bits out into the master. So in that sense, they are full duplex. Yes. Shift registering. Shift register. Yeah. Full duplex. Sure. Because you got outgoing and incoming bits at the same time, so they're full duplex. Which of these are full duplex? SPI and UART, yeah. So now UART though is only full duplex. There's a caveat there. UART's only full duplex if both the receive and transmit wire are connected, which they don't need to be. So in the applied portion of this course, we actually had a case where, and I think it was in the first or second lab, where you only connect one of the wires because you only need half duplex. But generally, UART is, in most cases, in my experience, it's configured as full duplex. In an I2C channel, what is the value of the SCL wire when there's no transactions in progress? 1, logic 1, meaning it's pulled up through the pull-up resistor. Of course, the pull-up resistor is going to actually, it's going to cause a voltage divider though, so you're not actually going to be at VDD, you're going to be at less than VDD, because you're going to be dropping a voltage over the resistor, which is why the pull-up resistor has to be, sized reasonably to not cause too much of a drop in voltage compared to the power supply, but you also don't want to have that much leakage through it. So I think generally speaking, they use like a 10,000 ohm resistor for that. What's the result of one device driving? Oh, and by the way, if you have multiple pull-up resistors, though, because you have multiple devices on the bus, though, that will also affect that voltage drop. But again, that's assuming that every device has its own pull-up resistor. What's the result of one device driving a wire logic 0 and the other device driving the same wire logic 1 using a push-pull driver? Ah, that's bad. That's undefined. It's probably you're going to end up with a something in the forbidden zone between halfway between 0 and VDD. Okay, that's that. Let's move on to quiz 3, and we're really running out of time. If I can get through quiz 3 and 4, I think we'll be in good shape. I'll publish these, by the way, too, as well as all the lectures I haven't put on Blackboard yet for you to help you for studying. Obviously, the exam I didn't mention is open book, but you have a limited amount of time, so it's you probably won't have time to look up every question. So I recommend that you review these. So at the very least, you know where to look when you get to the questions. Okay, quiz 3 now. Okay, quiz 3. Quiz 3 was on control theory. So control theory is actually, we gave you kind of just an introduction to it. The first question here is, what is a linear time invariant system? Well, so a linear time invariant system is a differential equation, but it has to be a linear differential equation. You can have derivatives and integrals of different functions, time series functions, signals, time series, yeah, signals. Signal is a time series function. You can have derivatives and integrals of signals, and you can multiply them by coefficients, but you cannot you can't multiply signals together inside the LTI. And remember, an LTI doesn't change the frequency. So you have an input frequency, The frequency doesn't change, only the amplitude and the phase. Now you might say, you know, can I have another type of system that changes the frequency? Yes, but then it wouldn't be an LTI, and you wouldn't be able to use the. I don't think you can use the Laplace transform. I'm not sure, but this LTI is, you know, that's the restriction. So in this case, we can't like divide g, you know, derivative of g by the original, by g. We can't multiply the derivative of g times the g. We can't square g. So that's why those options weren't LTIs. What's the S domain form? I love the Laplace transform. It's so simple. Basically, if you do a derivative, you just multiply it by s. You change the t to an s, and you make the functions capital. That's it. If you do an integral, you divide by s. So, and if you have a multiply scalar, you can just leave that in. So yeah, doing S domain for an LTI at least is easy. Now, if you're not doing an LTI, then the S domain, the Laplace transform can get a lot more complicated. Which of the following is a method for determining if a system is stable? You check the impulse response of the transfer function, and the impulse response is great because remember that the impulse response has infinite magnitude, and it has an infinite number of frequencies all mixed together. It's crazy, right? So if your system doesn't diverge from that, then it's stable. Which of the following are valid eigenfunctions of the function? So, you know, this, in order to do this, you have to get the function, the transfer function, into the form where you can do the eigenfunction transformation. And so in this case, we had to basically take the denominator here and decompose this fraction, 1 over s minus 8 times s plus 7. This has to be decomposed into a over s minus 8 plus b over s minus 7. Why is that? Because that's the form. So, you know, constant over s minus constant is the form that allows you to do the inverse Laplace transform, which gives you an exponential function, which is the eigenfunction when you go back to the time domain. Yeah, so you have to decompose it the way I showed you. The problem with this method for decomposing is the roots have to be unique. You can't have the same root. So if you had s minus 8 times s minus 8, then it wouldn't work. There'd be another method you have to use. What's the transfer function? Feeding the function 1 over s plus 1 over into the function s over s squared. Multiply them. That's it. You're designing a cyber. Right. You're designing a cyber-physical system to counteract the movement or blah 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 blah. What's the S domain transfer? Basically, you just have to convert it to a time domain differential equation, and then multiply everything together in the S domain. That's it. And then finally, yes, you also need a transfer function. Remember, is the output divided by the input. It's in that form in the S domain. And so the idea is that the transfer function gives you function over function on the left-hand side, or one side, and the other side is just everything in the S domain, ratio of polynomials in the S domain. Okay, PID controller, pretty simple, just proportional derivative integral. These are just multiplied by, proportional is a constant. The derivative is multiplied by s, and the integral part is multiplied by 1 over s, and then you just have to transform it into a ratio. So this is just algebra. Tustin transform is when you take the S domain and you substitute for s, you put in 2 over t multiplied by z plus 1 divided by z plus 1. This is really neat how this works. This ends up, I didn't go into how this is derived. But this is kind of neat. It's basically, it's converting it from discrete from continuous to discrete using a triangular way to basically do the integration. If you're interested, you should look that up. It's really cool. But for this exam, you just have to remember, how to do the test and transform. It's just basically substituting a value for S, or expression. Closed loop transfer function, all you have to remember here is the transfer function is the open loop. This is a closed loop transfer function. So you take the open loop, which is everything in the connected serially multiplied together, divided by 1 plus the open loop. That's it. That's all you need to know. In the class, I derived that. I did derive that in class, but that's the only thing you have to remember for the exam. Discrete time domain implementation of the transfer function. This is in the Z domain. Okay, so for this one, you have to basically do some math here in order to get. Your goal here is to get the output function on the left-hand side, and on the right-hand side, everything should be multiplied by something times z to the negative first power or below. So that way, because the idea here is that z to the minus 1 is the value of whatever you multiplied it against one sample ago. So f of z times z to the minus 1 is the previous value of f, and then multiplied by 3. Same thing applies for g. So you just have to make sure that you don't have any positive exponents of z in here, essentially, because that would require you to look into the future, which you don't know the future, but you just know the current value of g. You know the current value of g, sorry. So you can get the current value of g, and you can get any previous values of f. And the reason for that is because g is the input and f is the output. So yeah, so scratch that. Sorry, you can actually get the current value of g. In this case, though, in this example, though, there are no cases. All the g's are looking at the past in this example. But you can look at the current value, g of t. It doesn't have to be g of t minus 1 or earlier. Okay, so that's it. Sorry I went through that fast. I wanted to get through everything, and I just about ran out of time. So so I'll go ahead and post. See, the next chapter was real-time systems. Basically, the idea was the schedulability test was the main topic there, as well as understanding that there's deadlines, and when you scheduling is an NP complete problem because there's a exponential number of ways you can arrange the ordering of tasks. So that's basically the main point there. I'll put the lecture slides, though, online for the quiz. Or actually, they're already there for quiz 4. I still have to post quiz 1 and 2 because I just wrote those today. Because previously, I think I just, when I went over it, I just followed the actual Blackboard. So I'll put all that up, and I'll put all my lectures on Blackboard. If you have any questions, feel free to ask. And good luck on the final, and hopefully we'll see you all next semester. Have a great summer. Oh yes, Lab 3. When's the cutoff for Lab 3? Charles, do you remember? Do we give a cutoff date?
Oh, I think it was something with the school where I thought that after reading day you weren't supposed to have any assignments or anything.
Yeah. So normally I think we typically, I don't think we put in the syllabus this semester, but typically the cutoff is either reading day or the day before, right?
Yeah. Normally, I mean,
yeah.
From a practical perspective, I mean, I think Philip and I were going to get started on them this evening, so I mean, we're probably not going to get them all graded tonight, but. I guess it's up to you.
If you can get it submitted by reading day, that would be ideal. Just let us know. If you submit it late, make sure you email us because Dropbox doesn't tell us. Oh, yes. Yeah, Matthew. Yeah, I hope I see you. Thank you. Yeah. Yeah, I'm not sure if I'm going to be at graduate. I don't know what's going on with graduation. I guess we are having graduation, right? Curve, I don't know. I don't know about the curve yet. We're going to curve the final. I'm sure the final scores will be curved. I haven't looked at the state of the scores at this point, but it'll change after Lab 3 and the final. So it's hard to tell. But yeah, we'll definitely be curving because we did multiple choice. If you make one mistake on these multiple choice quizzes or exams, you lose a lot of points. So, the grades are lower than than ideally they should be. But I think that's just because of the format that we use. So yeah, there'll definitely be a curve. I just don't know what it is. I'm sorry, I can't predict that yet.
Also, be on the lookout, right? Because after we go back and grade all the stuff, we'll send out an announcement like we have before. And so once you see that announcement, we'll say, okay, we've graded everything we know about. So if you still are missing grades by then, you need to let us know, pretty quickly, so we can go and correct that before the final course grades need to go in. Don't panic until the email goes out, though.
I'm sorry, what was that, Charles?
I was just reminding everybody to be on the lookout for the email. Right
Email.
after we finish with grading, we'll kind of how we have. We'll put out an announcement of, okay, everything's graded. Make sure you have all your stuff, has scores on it, and if not, tell us, right? Because we only have a short amount of time to turn in the final grade, right?
Right. That's right. Okay. Sounds good. Thank you, guys. Hope you enjoyed the course, and I'll see most of you next year for 611, or in the fall, right?